Okay, hi everybody. I apologize if you listened to the recording I made earlier for the solutions to quiz 3. I forgot to plug in them. Oh, here I forgot to plug it in again. 'Cause I forgot to plug in the microphone for that recording, so the pen clicking is going to be loud and perhaps annoying, for which I apologize. Okay, but now we're all set. So what I'm going to do now is I'm going to move on to chapter 9, which is the last chapter we're going to cover this semester. You might be happy to know that. And this is going to be trees for PL. Remember trees? So what we need to do is to expand our truth tree method to accommodate the new features of the language, because we want to be able to test sets of sentences of PL for quantificational consistency. Remember that the tree method is, come back, the tree method, why is you not working? Sorry about this. There we are. The tree method is a test for consistency. So the tree method for PL is going to be a test for quantificational consistency. The tree method that we were using for sets of sentences of SL was a test for truth functional consistency. So we're going to have to, as I said, we're going to have to expand the method to accommodate the new features of the language. And so if the sentences in the set that we're testing are merely truth functional combinations of atomic sentences of PL, then we could just, we're all set with the decomposition rules that we had for the truth functional connectives. And what do I mean when I say if we just had sentences that were truth functional combinations of atomic sentences of PL? So remember that an atomic sentence of PL might be something like, why are you not working well? FA and, I'm not sure why this isn't working well. FA and say RAB, something like that. This is a truth functional compound of atomic sentences. So if this, for instance, were our only set member, then we could just apply. So you have to remember. You're going to have to go back and review the decomposition rules for truth functional logic if you can't. If somehow they've gotten hazy for you. So this we would have gotten from 1 by conjunction decomposition. And these are atomic sentences. So you also have to remind yourself what an atomic sentence of PL is. An atomic sentence of PL is just a predicate letter filled in with the appropriate number of constants, right? Okay, so if we only had truth functional combinations of atomic sentences, then we would be all set with just the the decomposition rules for truth functional connectives. So again, go back and review those. There were 9 of them, but now we may very well have sentences in our set that are universal or existential quantifications. So a set of sentences of PL might turn out to be consistent or inconsistent, quantificationally consistent or inconsistent on grounds other than truth functional ones. So let's take a look at a simple example. FA not GA, and for all x, if fx, then gx. Okay, so 3 sentences. This says A is F, this says A is not G, and this says everything that's F is G. So I don't think you'd have to think too hard about this one to recognize that this is quantificationally inconsistent. I hope that it's pretty clear to you that it's an inconsistent set. So what we want to be able to do to show that this is inconsistent using the tree method is we want to be able to decompose the universal quantifier in order to reach that inconsistency. And we'll do this in just a moment. But we're going to need some new rules, and I'll let you think about it for a moment, thinking about how many new rules are we going to need. Well, we're going to need one rule to handle sentences of this form. We're going to need one rule for universal quantifications, and we're going to need a rule for existential quantifications. But we're also going to need a rule to handle the negation of universal quantifications and the negation of existential quantifications. So we're going to need 4 new rules. We're going to keep the rules that we have already. 4 new rules, decomposition rules. Added to the 9 that we have already. The 9 for truth functional logic. Okay, so the rules for the negation of the quantifiers are actually pretty easy, because here's what those rules are. So one is called negation existential decomposition, and the other is negation universal decomposition. So let's think about, I don't know why I put those in there. Let me get rid of those. Negation existential decomposition and negation universal decomposition. Okay, so negation existential decomposition tells us that when we encounter the negation of an existential quantification, and these are all metavariables, right? This P is a metavariable where P is some formula that's got free X, okay? So when we encounter the negation of an existential quantification, what we do is we push that negation sign through, and it turns into this. That's all. So when we have the negation of an existential, we apply negation existential decomposition to it, and that's the result that we get. And negation universal decomposition, not surprisingly, is going to, not for all x, P, where P is some formula with free X. We push the negation sign through the universal, and it comes out the other side, but turns into an existential. So this is the existential decomposition, negation existential decomposition rule. This is the negation universal decomposition rule. When I said that these rules are simple enough, what I hope you see is that what you're writing down when you decompose the negation of a quantification is something that's equivalent to the thing that you've decomposed. So this sentence is equivalent to this sentence, and this sentence is equivalent to that sentence. If you think back to, remember we were talking about upward and downward correctness of rules for when we did the adequacy proof for the tree method for SL, and if you think about these 2 rules, they're both upward and downward correct. What does upward and downward correct mean for rules for PL? It means that any interpretation that makes the sentence that you decompose true is going to make the thing that you generate true. And clearly this is downward correct, and also it's upward correct because these 2 are equivalent to one another, and similarly these 2 are equivalent to one another. It's likely that we're not going to get to the adequacy proof for PL. In fact, I can assure you we're not going to. I may decide to post it on Canvas for people who are interested, but we're not going to go through it. But I thought I'd mention something about that. Okay, so those are 2 of our 4 rules that we have to add to the 9 rules that we had for truth functional logic. Let's think now about how we would handle, going back to this example I wrote down before, how are we going to handle universal quantifications? That is, what is this rule going to be, the rule for universal quantification? So let's think about a universal quantifier. If a universal quantifier is true, a quantification is true, then every substitution instance of the quantification is true too. I'm not sure whether I talked explicitly about substitution instances. I know that the book talks about them, but I don't think I did any examples, nor did I include any problems on a quiz about substitution instances. But let me just remind you, what is a and you may want to go back and look at the section of chapter 7 again. What is a substitution instance? So suppose we had everything in the universe is F. A substitution instance of that would be you lop off the quantifier and you replace the variable with A. So this is a substitution instance of the universal quantification. Why is it a substitution? It's an instance of it because this says everything is F, in particular A is F. And we're what's called a substitution instance because we're substituting A for the variable. Okay? So getting back to sort of thinking more abstractly now, if a universal quantification is true on an interpretation, then every single substitution instance of that quantification is true. If everything is blah, 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 well then, if this thing is in the universe, well then it's blah, blah, blah. If that thing's in the universe, then it's blah, 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 and so on. So every single instance of a universal quantification is true. So what we want is a rule that's going to allow us to write down a substitution instance of a universal quantification. So let me write that down, what I just said. So if a universal quantification, of the form for all x, whatever, is true, then every single substitution instance of it will be true. Every single substitution instance of it is true. So thinking back to what we're doing when we decompose sentences in the tree method, when we were doing trees for sentences of SL, we were asking ourselves, let me just put down a particular example. So this is just to remind us. Suppose that these were our set members, right? What we do when we decompose a sentence is we're back in SL, we're saying, okay, if there were a truth value assignment that made all three of these sentences true, what would it have to do? Well, in the case of A and B, it would have to make both A true and B true, right? Because we applied conjunction decomposition to line number 1, right? Okay, so if there were a truth value assignment that made A and B true, it would have to make A true, it would have to make B true. If there were a truth value assignment that made this true, it would have to make C false, and if there were a truth value assignment that made this true, it would have to make A false, right? So what we see in this little tree is, oh, wait a minute, we have a literal and its negation. There can't be, we conclude from this tree, no, there can't be a truth value assignment that makes each of those set members true. Okay, so when we are constructing trees for sets of sentences of PL, similarly, we're asking ourselves, what would an interpretation have to look like if it were to make all of these set members true? So going back to this little example here, we're going to ask ourselves, if there were an interpretation that made this true and this true and this true, what would that interpretation look like? And we would have to figure out, we would have to have the rule for universal decomposition in order to handle this member of the set. And what is that rule going to look like? It's going to look like this. Universal decomposition. If you've got a universal quantification and you want to decompose it, what you do is you write down an instance of that universal quantification, and the way that I'm going to write it is the same way the book writes it. This is a substitution instance of the universal quantification, where we've put in the constant a for the variable x and lopped off the quantifier. So if everything is blah, 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 well, then in particular a is. Okay, so that's the rule that we're going to use. So I think the best way to get a sense of what's going on here is to do this example. I'll start out with this very simple example where everybody kind of recognized, I think, that this is a quantificationally inconsistent set. Okay, so what we do when we have a universal quantification is we write down an instance of it. So there's something interesting about universal decomposition, and that is we never check a universal quantification when we've decomposed it. Why is that? Remember that when we quantification. Remember back in trees for SL, we did check sentences. I don't know why I'm coughing. Really, I'm not sick. I hope not. We did check sentences after we decomposed them because we're sort of done with them. We're saying, okay, if there were a truth value assignment that made this true, it would have to make A true, it would have to make B true. Done with it. We've dispensed with it. But things are a little bit more complex with quantificational, with the rules for the decomposition rules for the quantification for the quantifiers, because theoretically there's an infinite number of instances for any universal quantification. There are theoretically an infinite number of instances. So we never check a universal quantification. We can always go back and reinstantiate, write down yet another substitution instance of that universal quantification, and there are going to be times that we'll see where we're actually going to do that. We need to do that. Okay, don't worry about that. It'll all become clear. Okay, so let's do this example. Back to the set that we were looking at before. There were three members of the set: FA, not GA, and then finally for all X, FX horseshoe GX. And as I said, I'm hoping that it's obvious to you guys that these three sentences form a quantificationally inconsistent set. And why is that? Because if you've got something in the universe of discourse that we're calling A, that's F, and that thing is also not G, then it couldn't possibly be the case that everything that's F is G, because A isn't. A is F, but it's not G. Okay, so let's think about how we're going to finish constructing this tree so we get the result that we should get. Okay, so we're going to apply universal decomposition to line number 3. And what do we get? Well, universal decomposition tells us that we can write down any substitution instance at all that we like. So we could write down any substitution instance. We could write down FB horseshoe GB, or FC horseshoe GC, or FD horseshoe GD, right? Here I've put in B for X, here I've put in C for X, here I've put in D for X. Any one of these moves would have been completely legitimate, but it didn't really make any sense, right? Why would we introduce a new constant to our tree, right? Because what we recognize when we see that these three sentences form an inconsistent set is that well, if A is F and A isn't G, well, that's enough to show that this couldn't possibly be true. So let me erase. So the instance that we want to write down is the instance that we get when we put in A for X there. So we're going to write down FA horseshoe GA, and we get that from line 3 by universal decomposition. Got it? This says everything in the world is such that if it's F, then it's G. Well, in particular, if A is F, then A is G. Okay? Now we've got a conditional here, and we're going to apply good old conditional decomposition. So yes, so just make sure that you review. I'm not going to take the time to review them in this recording, but just take a moment and review the decomposition rules for sentential logic. Okay, so remember that if you've got a conditional, you decompose it. You write it branches, and on the left you write down the negation of the antecedent, and on the right you write down the consequent. And we get this from 4. We do check this because we're applying a truth functional decomposition rule. We get that from 4 by conditional decomposition. Okay, now we've finished this tree, so to speak. We're gonna talk later about what it really means to finish a tree. But when we take a look at this, we've got FA on line 1, and we've got not FA here on the left-hand side on line 5. FA and not FA are literals of PL. This is an atomic sentence of PL, and this is the negation of atomic sentence. So you can close a branch when you've got an atomic sentence and its negation on a branch. And here I've got GA on line number 5 and not GA on line number 2, so that branch closes as well. GA and not GA are literals, so we have an atomic and its negation, and here we have an atomic and its negation. So both of these branches close, so the tree is closed. And what we conclude from that is, oh, there is no interpretation that makes these 3 sentences true. Because if there were such an interpretation, well, then this would have to happen, and that couldn't possibly be. Okay? I hope that's clear. We're going to do lots more examples, and it will become clearer as we proceed. So we've gotten through, so we said that we have to add 4 rules, 4 new rules. A rule to handle universal quantifications, a rule to handle existential quantifications, a rule to handle the negation of universals, and a rule to handle the negation of existentials. And we've got 3 of them. We've done this one, we did this one, and we did this one. We just backing up a little bit of sort of theoretical stuff. We saw that both of these rules were both upward and downward correct because we're writing down something that's equivalent to the thing that we're decomposing. What about universal decomposition? Is it upward and downward correct? Is it downward correct? Is it the case that every interpretation that makes a universal quantification true going to make the instance that we write down true? Yeah, because if a universal quantification is true, then every single instance of it is true. So it's it's downward correct. Don't worry. I mean, if you're thinking, oh no, what is she talking about? You know, this is really just for your interest. I'm not going to quiz you on this, so it is downward correct, but it's not upward correct, right? Because just because an instance is true on an interpretation doesn't mean that everything in the universe has whatever property you're considering. So it's not, interestingly, it's not upward correct. It's going to turn out to be upward correct enough in order for us to prove the adequacy of the tree method, which again I'm probably not going to do in a lecture, but I'll post it on Canvas. But I just thought I'd mention that. Okay. one more rule we need, and that is the rule for how to handle existential quantifications. Existential decomposition. And that tells us that when we've got an existential quantification, once again, we can write down an instance of that existential quantification. So for instance, there's something that's F. There's at least one thing in the universe that's F. Well, I'm going to call it A, right? So I get that from this existential quantification by existential decomposition. Okay, so there was this little detail that we never check a universal quantification when we apply universal decomposition. There's another detail, sort of a significant one when it comes to existential decomposition. There is a restriction on your choice of instantiating constant. There's a restriction on your choice of your instantiating constant. Instantiating, what I mean is this is an instance. We're writing down an instance of it. This is an instantiation of that. So that's a fancy new word. So FA is an instantiation of there exists something that's X. So the restriction is that A must be new. It can't have appeared on the branch. You have to choose a name that doesn't appear higher up on the branch when you apply existential decomposition. So again, existential decomposition tells you that if you've got an existential quantification, there is at least one thing such that blah, 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 well, then you have to choose a name. Okay, well, then A, for instance, is blah, 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 blah. The reason, and we do check an existential quantification, but we have this restriction, there's this proviso that A must be new, because we're saying, look, there's something or other that has the property blah, 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 blah. Well, I'm going to pick some arbitrary name and say, okay, that's the thing that has the property. Let me give you an example that I think illustrates why we have to choose a new constant, why A must be new. So let's take a look. Okay, so take another look at that. Let's take a look at an example. Here's our set. There's something that's F and G. And the second member of the set is there's something that's F and not G. Okay, so think about that set for a minute. Do you think that it's quantificationally consistent? And I'm hoping it wouldn't take you long at all to convince yourself, well, of course it's quantificationally consistent. You'd have to have a universe of discourse that's got two things in it, right? One of those things is F and G, and the other one of those things is F but not G, right? It can't be satisfied. We couldn't have a one-membered universe of discourse that makes both of these true. We'd have to have at least two things. But yeah, it's not at all hard to think of an interpretation that makes both of these true. Do you want me to give you that interpretation? It would be something like, we have two things in it. We put one into both F and G, but we, we put one into both F and G, thereby making this true. That's the thing that's F and G. But we also need to have something that's F but not G. So we're going to put 2 into F, but we leave it out of G, right? So both of these turn out to be true on that interpretation. But you'd have to have two things in your universe of discourse in order to make both of those true. Okay, so let's do a tree for this set and see what happens. Okay, so we're going to write down the set members. There's something that's F and G, and there's something that's F and not G. Okay. And these are our set members. So the first thing I'm going to do is apply existential decomposition to line number 1. There's something that's both F and G. I'm going to call it A. And I get that, I'm checking it, and I get that from 1 by existential decomposition. So just it's similar to when we were constructing trees for sets of sentences of SL, we were saying, okay, suppose there were a truth value assignment that made these set members true. What would it have to do? Da 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 da, and then we would decompose everything. One way of thinking about what we're doing when we construct trees for sets of sentences of PL is, in a sense, we're constructing the interpretation. If there is an interpretation, we're kind of constructing what such an interpretation would look like. And that interpretation is going to be a fairly simple interpretation. One real advantage to having learned this abstract method of constructing interpretations that I introduced to you, and I'm very happy to say that just about everybody used that method of interpretation rather than the one that was in the book or using natural language ones. If you understood that method, then that's going to make what's going on in trees now much easier to grasp. Okay, so on line number 3, we decomposed line number 1 and by existential decomposition. And now we're going to, on lines 4 and 5, we're going to decompose line number 3 by applying conjunction decomposition. So we get that from 3 by conjunction decomposition, and that similarly by 3 by conjunction decomposition. Okay, and now the thing that's left to decompose is line number 2. Now, suppose that I totally ignore the restriction on my choice of instantiating constant when I apply existential decomposition. And so I say, okay, there's something that's F and not G. I'm going to call it A. And I get FA and not GA, and I get that from 2 by existential decomposition. This is, no, I'm violating the restriction, but I'm doing it on purpose, okay? Why A is not new. A already appears, right? We've already used A. Okay, but I'm going to continue anyway, knowing I made this mistake. And now I'm going to decompose line number 6, and I get FA and not GA. And I get that from 6 by conjunction decomposition. And I say, oh, I've got GA here and not GA here. That's an atomic sentence. That's the negation of atomic sentence. These are both literals. I've got an atomic and its negation. It closes. Well, when a tree closes, what you conclude is that the set whose quantificational consistency that you're testing is inconsistent. But no, it's not. We made a mistake. And the mistake is due to not observing the restriction on applications of existential decomposition. Okay, so let's go back and sort of think informally about what happened here. We're saying, okay, there's something that's F and G. I'm going to call it A. Okay, so A is F and A is G. If that's true, well then that's got to be true and that's got to be true. Okay, now I've got this one. There's something that's F and not G. Well, wait a minute. I can't just what I'm doing when I'm applying existential decomposition is I have to choose a name arbitrarily. There's at least one thing in the universe that's F and not G. I'm already kind of prejudiced with respect to A. A's my guy who's playing the role of the guy who's F and G. I can't say, okay, well, that A, who I already know some stuff about, he's also going to play the role of the guy who's F and not G. I can't do that, right? The choice of instantiating name has to be arbitrary in that sense. I can't choose a name that I already kind of know some stuff about and I'm prejudiced with respect to. So let's take a look at what this tree is going to look like if I did it properly. I'm going to redo the tree, okay? So now on line 1, there's something that's F and G. And on line 2, there's something that's F and not G. Okay, those are my set members. On line 3, I'm going to decompose line number 1. There's something that's F and G. I'm going to call it A. Because what I'm doing is I'm saying, you know, I'm going to see whether I can construct an interpretation that makes these two true. There's something that's F and G. I'm going to call it A. So A is my guy, who I'm saying is F and G. And I like to choose I like to choose sort of the alphabetically first name that's available to me, and A is available. So I get that from 1 by existential decomposition. And now I decompose line number 3 by conjunction decomposition, and I get FA and GA, and I get that from 3 by conjunction decomposition. And now and I check that, right? I'm done with it. The reason I can check it is there may only be one thing that's F and G, and A is playing the role of naming that thing. Okay? There may be more, but there may only be one, because that's the existential quantifier just says there's at least one. There may only be one. And now I'm going to go ahead and decompose line number 2. But I have to choose a new name. We saw that if we didn't, we got into trouble, right? This is the wrong answer. We got the wrong answer because we violated the restriction. Here, we're going to do better. We're going to pay attention to the restriction. And now I'm going to choose a new name, B. There's something that's F but not G. I'm going to call it B. B is going to name the guy in the interpretation he's going to play the role of the guy who's F and not G. And I get that from 2 by existential decomposition. And that's kosher, right? That's good. I used a new name. No violation of the restriction. And now I'm going to decompose line number 6. I get FB, not GB. And I get that from 6 by conjunction decomposition. And, everything that is decomposable has been decomposed, right? That's been decomposed, that's been decomposed, that's been decomposed, that's been decomposed. The only thing that doesn't have a check is a literal. That's a literal. So line 4 is a literal, line 5 is a literal, line 7 is a literal, and line 8 is a literal. So this tree is open, which doesn't surprise us because we fully expected a tree for these sentences to be open, because we know that this is a quantificationally consistent set. Okay, so we got the right answer here. There's something really interesting about this, though. If we remember back when we were doing trees for sets of sentences of SL, we would collect the truth value assignments that we could from the open branches. There's only one branch here. It's open, right? So what I'm going to do down here is I'm going to collect the truth value. I'm going to collect the literals. The literals that I have on this open branch are FA, GA, not FB, not GB. I'm sorry, FA, GA, FB, and not GB. These are the literals on the open branch. So here's something cool about trees for sets of sentences of PL. From those literals, you can easily, there's kind of a recipe for constructing an interpretation from the literals. So this is a cool way of actually checking your work. It's also a cool way of constructing interpretations that show that sets of sentences are consistent. Okay, so how are we going to do it? These 4 literals suggest an interpretation with a universe of discourse that has 2 things in it. One of those things is named by A, and one of those things is named by B. So I'm going to have A name 1 and B name 2. Now I'm not having my universe of discourse have A and B in it. A and B are constants, so I don't want to make sort of a use-mention kind of confusion here. So I'm going to have A as my constant that names 1, and B is my constant that names 2. Now, in my interpretation that shows that these form a consistent set, I don't need to give reference for A and B because A and B don't appear in those. But these are the literals that I generated when I did the tree. So this basically gives me a recipe for constructing the interpretation. What do I do? If I think of A as naming 1 and B as naming 2, this tells me put the thing that A names into F, namely 1, and put the thing that A names into G as well. Oh, shoot. Did I run out of ink or I ran out of ink? Oh, no. Hold on 1 minute. Hold on 1 minute. Hold on. Charge this for a second. Does this work? Go away. Go away. Go away. Go away. Shoot. Go away. How do I make that go away? Come on. Okay, good. Okay. Okay, that worked. I'm sorry. We put that. I'm not going to redo. Do I have to redo this whole recording because of that? No, of course not. Right? You guys, you're patient. Okay. So this tells us what it put the thing that A names into F. I did 1. Put the thing that A names into G. Okay, I'll do that. Put the thing that B names, namely 2, into F, but don't put it into G. Okay. And this is the interpretation that these literals suggest. There's kind of a canonical way of constructing interpretations from the literals that you get on an open branch. We'll do lots more examples, but let's take a look at what we got here. This interpretation is precisely the interpretation that you had in mind when I initially said, when I initially gave this example and said, well, of course this is a consistent set, but it's got to have 2 things in the universe of discourse. One of those things is both F and G, and the other one is F, but it's not G. And so these literals that we got from the open branch of the tree give us just the interpretation that we expected. And it kind of gave us the most streamlined interpretation that shows that these sentences form a quantificationally consistent set. Okay, I'm going to stop here. I hope that was clear. There were, despite the technical glitches. Let me just review what I did. We remembered what an atomic sentence of PL is. We recognized that we're going to need 4 new rules to accommodate the quantifiers, rules for the quantifiers and rules for the negations of the quantifiers. The negations are very simple. We just write down something that's equivalent to what we're decomposing. For the universal quantifier, there's a complexity, namely that theoretically there are an infinite number of instances. We had to remember what we mean by a substitution instance, right? There are an infinite number of substitution instances for any universal quantification. So we'll see examples of why it is that we may want to go back and reinstantiate. We never check a universal quantification because we may want to reinstantiate. We did an example using universal quantification here, and we noted that, of course, we're going to instantiate using the same name that we already have up here. We'll revisit that later on as well. Then we introduced existential decomposition, noted a different complexity, namely that our choice of instantiating constant when we apply existential decomposition has to be arbitrary because there may only be one thing that has whatever property follows the existential quantifier. And so we can't choose a name that we already are prejudiced with respect to, that we already know some stuff about. It has to be an arbitrarily chosen name. We looked at an example that shows that, oh, wait a minute, this is exactly why that name needs to be a new name, because we may end up very well with the wrong answer if we don't observe the restriction on existential decomposition. This tree closed when it ought not to have closed. This tree should be open. We did the tree correctly, and sure enough, the tree was open. And then we took a look at the literals that appear on this open branch and saw how we can use those literals to construct an interpretation that actually makes the set members true. So I'm going to stop here. There's lots more to be done, but this gives you kind of an introduction to trees for PL, and we now have for the decomposition rules, we have all the 9 truth functional decomposition rules. So just make sure that you remember those, plus 4 new ones. So we have a total of 13 rules. You already know 9 of them, and these you'll very quickly learn how to use. So I'm going to stop here. I'm going to pick up from here on the next recording. And okay, until next time. If I can figure out how to turn this